Good afternoon, everyone. I hope you can hear me well. I certainly do. Well, my name is Susana. I'm a geophysicist at Galp Energia. I work at Galp for 3 years now as a junior geophysicist. And, well, I'm responsible to follow up acquisition and processing projects, also gravity and magnetics, and Matlab. And you may ask, why do we need Matlab in Galp and in Geoscience? Well, despite we have really powerful exploration and production tools and softwares, usually we also need to be able to build our own user-oriented tools. Why? Because, well, especially in geoscience, we have lots of methodologies coming up. I don't want to say every day, but almost. And we want to be able to track these new methodologies, to be able to use those new methodologies at Galp. And of course, to fulfill the needs and the strategy of the company. And of course, these softwares are really expensive, and we should have an alternative to those softwares. Well, you will see that I will present those standalones that were produced in Matlab for the last 3 years. And these standalones cover a broad spectrum of topics, namely geology, geophysicist, petrophysicist, and also geochemical. And nowadays, we are also thinking that we have a large amount of data coming in, especially in exploration and production departments. So we are thinking on using also Python to cover some limitations that Matlab has, and also to be able to freely work with a large amount of data. So this was the brief introduction. I will talk to you about some examples of standalones that were produced at Galp. 5 examples of the standalones, since I believe that most of you are not familiar with geoscience fields. I will do a brief presentation of each tool. So let's start with fluid substitution. What is this? Well, it's pretty obvious if you think of the word. Fluid substitution is simply when you have a reservoir that is filled with some fluid, and you want to know what happens if that fluid is something else, other fluids. So let's imagine you have a wave propagating through the medium. That wave and the velocity that it propagates will depend on the density and elasticity of the medium. Well, we know when we work with 2 types of waves: compressional waves, or P waves, which are really dependent on the strength of your material and the fluid in it. And you have the shear wave, or the S wave. Well, those waves do not propagate in fluid. And this is very important to think about. Why? Because if I have a drilled well, and I have data, and I know the lithology of that well, I know the data because we measure that, and I know I have a reservoir that is simply a rock, which is very porous and permeable, that can bear the hydrocarbons, and that's what we're seeking, of course. And imagine that in that well, my reservoir has water in it, but I want to search for the hydrocarbons, I want to search for the oil, I want to search for the gas. So what do? We simply replace the water in the reservoir by another fluid, for instance, gas. And why? Because in the end, we want to know if the properties, the physical properties like velocity changes when you change the fluid, and how does it look like on your data. And then you compare, and you may get to the conclusion that maybe that reservoir in another location may have hydrocarbons in it. So let's give you an example. This is the interface that we created 3 years ago at Galp to try to understand what would happen to the physical properties like velocity if we change the fluid in the reservoir. So we have 2 cases. One, I don't have any data. I'm just doing synthetic work because I don't have well data, but still I want to know which parameters will influence the physical response on my rock. And the other is I have well data, and I may import that data into the standalone and simulate what would happen to the velocity, for instance, if I change the fluid in it. So let's give you an example of what happens if I don't have any data. I don't have well data. This is a synthetic case. Okay, so I told you that I want to replace water by gas, for instance. Well, gas is less dense than water, as you know. So you see on the axis of the density, for instance, my initial density was higher than my density after I replaced the fluid by gas, which is lighter than the water. What happens to the velocity? I told you in the beginning that the compressional wave, or the P wave, is highly dependent on the rock, on the material that composes the rock, and also the fluid in it. Well, if I replace the water by gas, which is less dense than water, then my velocity will react to it and will decrease drastically because of this change. Well, in the other hand, S velocity or shear wave will not interact with the fluid, which means that you'll have a slightly increase in the velocity in S wave. And then we have also the Poisson ratio. This is simply a function of the S velocity and the P velocity. This is very important for us because you are seeing the both changes at the same time. And then we have what we call reflection coefficient. This is nothing more than a function of your density and of your velocity. In the end, what we see in the seismic data, when we acquire the seismic data, this is what the geologists do when they are interpreting, is a function of velocity and density. Is what you see that in the gather axis, a change on the amplitude of the wave, because I forgot to tell you something. The seismic data is this reflection coefficient convolved with the signal of the Earth. We know when we shoot seismic exactly the shape of that energy that enters into the subsoil. So if we convolve the shape of the wavelet, that's what we call, with the coefficient reflection, we get the seismic data. And if we have the presence of hydrocarbons, especially gas, we'll see a decrease of the amplitude in the wave through the angle or through the offset, which is quite the same. This is what we call AVO or AVA, which is anomaly versus offset or anomaly versus gathers. This is what we are looking for. So this is more or less the display, the final display that we have in case of purely synthetic case. So what if we have data? We have to bring in the data, which is a specially format, this last format, and then we do exactly the same. We replace the density of water, for instance, by another fluid, by oil or by gas, and we get more or less the same response. Look that, for instance, the gather is much more messy than we had in the synthetic case. This is a real case. This is not really pretty. So this is the fluid substitution. And you may understand why this is important for us. Because we, in the end, want to reach to a location when we have the hydrocarbons. We want to drill and to be success and to find hydrocarbons in our reservoir. So that's it for the fluid substitution. Let's move on to another interesting subject, POS, or probability of success. This is a quite important issue. Why? Because the companies, oil and gas companies, rely on this value to rank their projects, for instance, to know if that prospect or that project is good enough or is good enough for it to be drilled. So you even calculate your expected monetary value based on this POS value. So what is the problem with the POS value? is that POS value is estimated is a really subjective estimation by the companies, by oil and gas companies. And this is a problem, because if you rely on a value that is highly subjective and depends on company for company, because it depends on the expertise of the team, it depends on how successful was your company drilling wells, it depends in so many ways. One guy, Milkov, in 2015, created or published an article which proved that this subjective assessment is really an issue for the companies. If you give the same prospect to a company A and the same characteristics to a company B, for sure the value, the POS value, will be different. And we rely on this value whether to drill a well or not. Calculate the volumes, for instance. See if there is commercial, if it is commercial enough to drill, for instance. So, before I explain you that part of the prospect, because this is important for you to understand, is that, okay, what is a prospect? Basically, is when you have to prove that a petroleum system works. You have your source rock, which is your mother rock, where you produce your hydrocarbons. Under certain conditions, those hydrocarbons will crack and will migrate to your reservoir, which is the porous and permeable rock that will hold hydrocarbons. And then you have a seal above it that will prevent the hydrocarbons to migrate, and the trap, that is a system composed by the seal and the reservoir that catches the hydrocarbons in that rock, in that reservoir. So this is very important. What we have to do to assess this POS value is to evaluate each risk factors, which is the source rock, which is the reservoir, the seal, the trap, the timing and migration of my source rock. And so Milkov, when he did this study and proved that subjectivity was a problem, he created the risk tables, which are lookup tables with checkbox that give us an objective value based on the data that we have and the models that we have. So basically, these are the risk factors from Milkov, and then I just mimic the risk tables from Milkov. So, for instance, a really simple one risk for you to understand is the presence of reservoir. What is this? Okay, I have my data. Do I have wells? Do I have seismic? What do they tell me? Do I have reservoir facies, or I've proven that the reservoir facies exist by the well, for instance? So do I have nearby wells near my location? Can I prove that in my location I have the presence of a reservoir? Okay, let's see the model as well. What type of ambient was that reservoir built? So let's suppose, okay, this is a reservoir that comes from a marine environmental, and this is carbonates. And I know from my well data that nearby wells proven the existence of that same reservoir, so probably my reservoir exists in my location. Okay, good. Then I give a 1. I'll do the same for all of the 6 risk factors. And I came up with this. This is the outputs that were created based on what the users wanted, what the exploration team wanted. So basically what you see there is that bars are the POS, or the risk that each factor was given by the users by selecting in the checkbox what was more suitable for that project. And then you see what we call the horn diagram. Basically, what is the horn diagram? You see the x-axis is basically the risk, and the y-axis is the certain. How certain are you of the value that you are given? And then we plot this. We have 6 stars, in this case 6 stars, which will be multiplied by each other and give a single prospect POS. This is what will be used to say, okay, I want to drill, or no, this is too risky. And then we also have created what we call like an Italian flag, which is tell me the negative evidence about your factor and your positive, or there's nothing to say. This is very important because we access lots of prospects, and 3 years from now or 4 years from now, you won't remember. So it's good to keep track of why do you or did you have that answer. So this is POS. I'm going too fast. Let's go for the third standalone that was created by us in Galp. Well sheet, that will be an easy one, I promise. Well sheet is really simple. In Galp, we receive every day lots of data. Especially in exploration and production departments, we need to keep track on lots of data, especially the well data. So we have lots of teams working on tracking those data, of course with different tasks. But we felt the need to build a sheet that could aggregate important information about that well. Why? Because we want to keep it simple to every exploration and production department to access important information. What happens, the problem was that they were building these well sheets in Excel. It would take hours, if not days, to build a single sheet. Imagine doing that for hundreds of wells, for instance. It was impractical. So what happened was the petrophysics team came to us and said, please see if there is a way for, in Matlab, to build an interface of these well sheets and save them and print them, so we can do that for all the in-house wells, so everyone can access the information easily. And I was like, let's try this. And it was pretty simple. As you can imagine, it's just, okay, grab lots of information, either Excel files or image files in various formats, put everything in a single sheet, or in a single folder, which would be the folder of the well. You just select it, and then voila, you have your well sheet reporter, which will be something like this. This is the well sheet reporter example. What you see here is a compilation of several files inside the user-oriented tool that they want to, okay, put this, that, put this here, and that's what we came with. This is the back part of the sheet. That image that you see down here is what we call the seismic data. This is our seismic image. This is what the geologists are interpreting to find oil or find gas. This is very important for us, of course. So you see, with these standalones, we are able to reduce time-consuming tasks. They took hours to build just one. We took like 2 seconds, and I'm counting the time that you spend searching for the folder. So it's an amazing tool. The output, of course, you can save it as a TIFF file, for instance, and print the well sheet. Now we're going to the Atlas. Okay, this is, well, I told you in the beginning that I'm a geophysicist, and I talked to you about the seismic data. Seismic data responds to difference in density and elasticity of the medium. Well, the gravity and magnetics is different. Gravity responds to contrasts of density, while magnetics responds to contrast of magnetic susceptibility. So let's imagine, it's pretty simple, okay? Let's imagine we have a rock, really dense, and with lots of ferromagnetic minerals. Well, okay, beneath me, okay? What happens? I'll create an anomaly, a positive anomaly, both in gravity and magnetics. Why? Because I have a really dense rock around less denser rocks. The surrounding is not that dense. And also, the magnetic susceptibility of that rock is also higher than your surroundings, so you'll create a bump, a positive anomaly. But I don't really want just that bump. I want to be able to locate that body. I want to know the edges of that body. That's what really interests me. Because I want to know, is this a fault? Is this a volcanic rock? I want to know in my data. So there is a way to do this, of course, by enhancing the data. And you enhance the data by applying filters to gravity and magnetics outcomes. One of the filters is pretty simple to understand. The horizontal derivative, for instance, is just will give you the major contrast of the high and the low. So you'll have the edges of your body. The same goes for the vertical derivative. And we know that, for instance, the maximum of the horizontal derivative give you the edges of that body. The same goes for the tilt derivative. The zero contour gives you also the edge of the body. So in 2015, Cascon simply created a method, an automatic method for selecting those edges of the bodies by overlaying both the horizontal derivative and the tilt zero. And this is pretty good because I spent lots of time picking those alignments in ArcGIS was an horror. And then I thought, why not? I'll do the same. Okay. So what do we do? We simply load the data. It's an horizontal derivative, a tilt derivative. You just put it in the system. It's in XYZ format. It's pretty simple to read in Matlab. And then, okay, this is my data. This is an example. This is gravity of the horizontal grid on the top. On the bottom, you have the tilt derivative. So in red dark color above, you have the maximum of the horizontal derivative. Below that dot, that black dots, are the zero contour of the tilt derivative. We may change those parameters because I have to do some assumptions to do this calculus. How do you get to the maximum of the horizontal derivative, for instance? So I may change this. I said, okay, let's put a Gaussian with my data, and now I say that more than 75% of my Gaussian curve is the maximum. And then I say, okay, my zero contour is my zero, but many times you don't have a zero contour of the tilt derivative. So you have to make assumptions. You have to go to grab your lowest value near zero, for instance. You can play with those values by right-clicking or double-clicking on the axis, and you may change for the suitable value that you think represents your data. And then what we do, we simply overlap the maximum horizontal derivative with zero contour tilt, and voila, we have our alignments. It's pretty simple. And then I came up with a really nice tool, which is, okay, a kind of a windrows that will give me the preferential alignments of what I just picked, which is very nice for the geologists to know the preferential direction of faults, for instance. So this is Atlas. Pretty simple, pretty user-friendly, and of course, it takes a lot less time that it would take if I had to pick that by hand on an ArcGIS software, for instance. And finally, last but not the least, geochemical log analysis. What is this? I told you in the beginning that E&P softwares are very complete, but they are also very expensive. And of course, because they are very expensive, the licenses are limited. So what happens is, sometimes you see users using Excel, for instance, to load data and to work with data. This is a problem because sometimes you may mess with the data. We don't want that. The data shall be kept as it is. You cannot mess with that. So I had a request from our colleagues from Bayesian Modeling to build a tool that could display the data that they want. They want to see well data, they want to see Excel data. And then to be able to do some calculus, their own things. I don't ask, I just build the tool. And basically, these are the data that I have to input in my interface. And these are some of the functionalities that they requested. to input several files, because sometimes I don't want to see just one well, I want to see several wells to compare. Or save, this is an important one, save as temporary files, because you do lots of work. Sometimes you want just to save this and load afterwards to keep on working. A calculator to do lots of calculus that they want to do. Overlay logs, swap axes, lots of functionalities. This is the look of the interface. This is an ongoing tool. It's almost finished, actually. This is the example of the calculator. You have lots of tracks there. Of course, you may do whatever you want, change the color, swap the axis, whatever you want, change the vertical scale, lots of functionalities. And this is another example of a user-oriented tool. This is very important for us. And now, leads me to the final remarks of this presentation, and this was pretty fast. We can actually benefit from these Matlab tools because we want to be able to build our own user-oriented tools, because we want the users to have the opportunity to experiment new methodologies if they want, because it just came out and they want to experiment those new methodologies and they don't have any idea how. So we can build this. We can also reduce time-consuming tasks, as I explained you before, with the well sheet, for instance, or with the ECLAS methodology. And as I told you before, we are thinking on going to Python to overcome some issues related to mostly portability of the standalones created in Matlab. That was one of our bigger issues, and now because we want to do some more heavy programming with the big data that we have in-house. And that's it. Thank you very much.
Any questions? Yes, sir. Looks like there's a question.
Oh, nice.
A very nice presentation. Thank you.
Thank you.
I also work at Galp.
Oh, nice. Where?
Currently at procurement.
Procurement, nice.
But I'm a chemical engineer, so
nice.
I understood a little bit. So I was wondering, you said we were talking about big data, but how much?
Too much. Let's see, for instance, seismic data, you can have like teras of information with the seismic data. It's a lot. And we work a lot. We have lots of issues with the memory, for instance, just to have accessibility for this. It's really a lot. That's why we want to be able to do some programming using more user-friendly tools for that. Because Matlab has a lot of memory issues as well. I tried once just working with a single seismic line, and we work with lots of seismic lines, and I couldn't run a simple geostatistical test that I was doing because problems of memory, for instance. So that's why we are trying to migrate to Python. Thank you. Nothing more? I should brought the t-shirts like the other guy. Thank you very much.